welcome to one and all invited here. This is Sai Krishnan, pursuing my engineering degree in the Department of Electronics and Communication at Chennai Institute of Technology. We are analog beings living in a digital world, facing a quantum future. Chennai Institute of Technology, the college has not left any stones unturned in making its students worthy citizens. The time as a caterpillar has expired and the wings are ready. Yes, it is all about transforming lives. It's been just 10 years since CAT has stepped in, but the victories are huge under the successful guidance of our Honorable Chairman, first generation entrepreneur, Shri P. Shriram. It is indeed a privilege for all of us to get the opportunity of attending these webinars. To be short and crisp, yes, it's all about Knowledge 4.0. Today, we have our expert Dr. Sachin Chowdhury from IIIT Hyderabad and our organizing secretary, Dr. Malati. I feel much pleasure in welcoming you all. Now, I request our organizing secretary to give a brief introduction about our session. Please, ma'am.
Yes, ma'am. Thank you. Good morning to one and all. One and all. I welcome you all for the fifth day of our STTP, AICTE sponsored STTP. I thank Dr. Sachin Chaudhary sir for accepting and give the deliver for our STTP. Today, sir is going to deliver on the lecture of communication technologies in IoT. I hope you can get very much knowledge on the, there is a, you can have a great session with SARS field. I ask Sai Krishna to give the introduction about her sir.
Yes, ma'am. Speaking about our guest profile, Dr. Sachin Chowdhury has received his Bachelor of Engineering degree in Electronics from Visvesvaraya National Institute of Technology, Nagpur in 2002 and Master of Engineering in Telecommunications from IIC Bangalore. Initially, he worked at S-Cube Communications, a startup by IIC professors, as a senior wireless communication engineer. There, he worked on WLAN, VMAX, and TDD-SCDMA. Then, he did his PhD with Professor Visa Koivunen at the Department of Signal Processing and Acoustics, Aalto University. Then, since December 2014, he has been working as an assistant professor at IIIT Hyderabad. We feel much pleasure in welcoming you, sir. So now, without any further ado, I request you to take over the session, sir. Please, sir.
Thank you, Sai Krishna, for the introduction, and good morning to all of you. And my name is Sachin Chowdhury. So let me, and I'm going to talk about very interesting topic, communication technologies for IoT. And before I start my presentation, let me thank Dr. Malti and the organizers for giving me this opportunity. So here are some of my research interests. Maybe few more minutes on my research, my background. So my research interests are in the field of signal processing and machine learning for wireless communication, and particularly Internet of Things, 5G and beyond, and corporate radios. In the past, I have worked on European projects Sandora and ENCO2, which were on wireless sensor network and corporate radios, and and then I have also worked on a DST project, Indian government project on corporate radios for 5G, recently completed. Currently, I'm working on three IoT projects, and I will talk about them.
Sir, have you shared your screen, sir?
Yeah.
No. Now we are in live, sir. One more time, you can share your screen, sir.
Okay.
We cannot see.
Can you now see?
Yes, sir. We can continue, sir.
Are you able to see the changes in the slides? Hello?
You can continue.
Okay, fine. So I was trying to say that I currently I'm working on three IoT projects, and I will talk about them very briefly towards the end of the presentation. So here is the outline of today's presentation. So I will start with some basic definition of IoT and its motivation. And then, since it's a very broad topic, I will basically first define the scope of the presentation, and also to understand the today's presentation, I'm going to give very basics of communication, especially the MAC layer protocol. And then we are going to talk about, I will be talking about different wireless technologies which might be applicable to healthcare industry, or let's say IoT applications for healthcare. Now, keep in mind that obviously I don't have that much time that I can actually go in deep or depth of each of the technology. But the idea is that I will give you an overview or basically the philosophy, the way which different IoT or communication standards for IoT are adapting to, different communication standards are adapting to the IoT part. So now if you search on internet the definition of IoT, then you will get hundreds of definition and lot of mumbo jumbo and jargons. But if you want to understand IoT in the simplest of terms, then we need to look at the internet which we are using daily, right? Especially after the social media and even more after COVID-19, right? So what is internet? Internet is a interconnection or network of computing devices such as computer, laptop, servers, smartphones. So if you now extend this definition to the things of everyday use, then you get your definition of internet of things. Okay, so now I can basically extend here. I can put I can connect a bulb. I can connect here a maybe a fan, a cycle, right, or an iron. So anything of everyday use. So you might have a question that how do you connect the thing to the internet? So here is one example. So what we need to do is we need to insert a chip or attach a chip which will monitor control some parameter or physical parameter of the thing, right? So what we have to do then is like put an electronic chip like this which consists of either sensor or actuator and a microcontroller and a communication module along with battery. So this is very basic idea I'm giving about chip. A lot of things might go into a chip, but I'm just giving a very basic overview. So using this electronic chip, basically a thing will then talk to the internet. Now the next question would be, why do you want to connect a thing to the internet? What's the point in connecting a thing like a shoe, right? So this is one very interesting thing is that about IoT is that the applications of IoT are very amazing, but they are only limited by human imagination. Okay, so suddenly if you start putting sensors like GPS, camera, Bluetooth in this kind of a shoe, this can be used by a blind person to navigate comfortably in a basically city streets, okay, streets of a city. Even for a normal person, I will say that we can use, let's say, if we insert a pressure sensor in both our shoes, then over the time, if you see the pattern, then you will start saying that if there is a change in a gait or the way person walks, then you will already start understanding if the person is basically going to have some health issues regarding his leg, right? Because the balance is shifting. Right. So this is something I really find fascinating about IoT. So to be smart, a thing doesn't need to have super storage or it need not be a supercomputer. It just needs a connection to a super storage or a supercomputer. That will make it basically a super. That will make it as a smart thing or a super thing. Okay. And also, it is not possible to insert basically very expensive and very, let's say, super storage and computing power in all the things, because then the all of the things will become very expensive and you will not be able to connect things very easily to the internet. So I think that if you start connecting your phone, right, a device which is as powerful and as costly as your phone to everything, then the deployment will become very prohibitive, right? So this is how the IoT works, that you have sensors and actuators here. So sensors are sensing some physical phenomenon. They are sending data. Basically, they will connect. They will send data to the gateway, and from gateway it will connect to internet. And over internet, the data will be stored in some database or some storage devices, and then it will be, let's say, we can do some analytics over some analytics platform, and then you will get the data will flow back to some kind of actuators. For example, let's say you are monitoring your heart rate, and the data is going to the doctor, and if, let's say, some kind of person is getting basically a heart attack, then already the ambulance might already start coming, okay, before the actual heart attack starts. I'm saying already there might be symptoms. So this is one very good example of how does IoT work. Then here there are applications of IoT. So you can see the top one is a smart city. Then you have smart industry or industry 4.0. Then you have smart buildings, autonomous cars, smart grid, health is there, agriculture is there, many more. So basically, these are just top of the many applications. And you can see on the top we have smart city. And in India we have given special, the government has given special let's say attention for the smart cities by declaring the smart city mission, under which 100 cities have already been declared. So because of that, we have kind of came up with, we have established a center of excellence on IoT for smart cities at IIIT Hyderabad. I also want to mention here that although this slide, or let's say this figure is from 2018, and I feel that given the pandemic condition, the connected health is actually will come in top two easily. So I also feel that that way this seminar is very timely. So so IoT actually has now become a necessity. Okay, so if you see during the times of COVID, everything has actually gone online, right? So from our health to our education to our work, and in such scenarios, IoT can be of immense help. So I have taken here two basically examples. One is on health. So on health, basically we what we can do is we can do remote monitoring of COVID patients. Let's say we can monitor the temperature, oxygen levels, heart rate, blood pressure, uh, this kind of basically health parameters which are related to COVID. We can monitor them remotely, and we can do it continuously also, throughout the day. We can have some kind of a watch wearable where the watch is the wearable is taking the measurements continuously every 15 minutes. Second thing is you have telemedicine, so where basically instead of going to hospital, you can consult a doctor over video. So so what these two things are doing is they are taking off the pressure from the medical systems, okay, or our basically health systems, which are really stressed right now in this pandemic. Also, they can help in compliance, like are people basically maintaining social distance? Are they wearing masks? Are they doing that hand hygiene? Are they sanitizing often or not? Second thing is that the manufacturing industry, which has suffered huge losses during COVID, and now the important thing is to get back on the track instead of, so the industries are not focusing on actually earning more and more profit, but they are trying to get back and then get back to the manufacturing and try to survive. Okay, so in this particular case, IoT can help by basically uh, remote monitoring and control. The basic idea is that it will reduce the amount of people or the number of people on the ground by allowing this remote monitoring and control of the machines. Okay, so that you still need some people on the ground, but the number of people on the ground have reduced now. Okay, so then these are the issues in IoT from communication perspective. So you have basically the first one is the low power consumption. Obviously, if you have, let's say, many devices, so as I'm saying that there are a lot of things which we can connect to internet. So and you can't put all of them to the mains or plug points, right? And if you put so many devices in, let's say, keep battery, then in batteries, let's say going something like a phone, like every day you have to charge, again it will be very problematic. Or if you have replaceable batteries and if you keep changing them, if you hundreds of devices every other day, you will end up changing the battery. So so definitely what we want is we want that a uh, what we want is we want, hello, everything is fine, hello, okay. So so we don't want to change battery. So what we want in terms of power consumption is that the power consumption should be very low, so that a coin operated battery should last for years. Then, as I said, that the number of devices or number of the devices which are connecting to the are increasing. So in the let's say room itself, you may have 10 to 15 devices. In a home, you might have 100 devices, and in a building, you might have 1,000 devices, and on city level, you might have millions of devices. So what traditionally has happened is that uh, so traditionally what hello madam madam hello okay, I'm just getting some voices. So okay, so so traditionally, if you see what has happened in the wireless technology is that we are only trying to increase the, let's say, data rate of our technology. Or so, but let's say if I have 1 Mbps, let's say, hello, madam, hello, 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 hello.
Sir,
Yeah, can you mute your
sir,
mic? I'm getting a lot of voices there from there. Hello.
now I muted, sir.
Okay, thank you. Okay, so so as I was saying that generally what we are doing is we are trying to only increase data rate for few number of users. Let's say in either if you consider wireless LAN or if you consider cellular operators. But in this particular case, what we need is we need to support large number of devices, right? And the difference from cellular part is that in this particular case, each of this device have only few bytes to send once in a while. Let's say if you are monitoring a temperature, you might want to basically monitor every 5 minutes or 10 minutes or 15 minutes, right? And that too few bytes you need to send, not like mbps and gbps of data you are sending. You are only sending, let's say, hardly whenever you need, only kbps, that too only certain portion of the time. So the idea is that even if I, let's say, have 1 Mbps or let's say 10 Mbps I was giving to one user, and now instead of that I had to support 1,000 users with let's say 10 kbps. That's not, the scaling is not trivial, because we need to do a lot of synchronization, and there are a lot of data to be exchanged before there has to be some kind of synchronization between the different devices. Okay, so I want to say that scaling is not very trivial. Then you have coverage that, let's say, smart city, farms, all of them need pretty large coverage. So that's again a challenge. Then the quality of service is there, that you want. Some applications might need real time, let's say, uh, service, and some of them basically the latency has to be very low, and some of the application might tolerate latency. So that kind of issues are there. Some of the applications might need high data rates. Some of the application may be okay with very low data rates. Then I would like to highlight the privacy and security issue, in the sense that in IoT, for IoT to become, let's say, commonplace, say privacy and security are very important. Okay, so one example I would like to give for, let's say, privacy is that wearables. So I am using nowadays, I'm using this wearable watch, like a, which is like 3,000, 4,000 rupees, and which measures how many steps you are walking, and heart rate, and blood oxygen, and blood pressure, like say blood pressure also. So all this basically parameters the watch is monitoring, and it is connecting to my phone through Bluetooth. Now what I found that if I use a same app on the other phone, so anybody can actually download the data from my phone. It can connect to that watch and download it. And you don't want, definitely don't want your medical data to be, let's say, or your yeah, health data uh, to be stolen, or let's say used by people. So I think that is something very important. So privacy as well as security. And there again is a standardization issue, because everybody in IoT is coming up with their own solution and they can't talk to each other. So again, that's a big issue. So today's scope of, so there are several protocols on IoT, and today we will be focusing only on the communications protocol. And even there, if you see the communication protocol stack, you have, let's say if I consider this 5-layer internet protocol stack, you have so today we will only focus on physical and MAC layer. So physical layer, basically in the physical layer, what we do is we convert the bits into waveforms, which can be transferred over a physical medium. Okay, like Ethernet, it can be Ethernet or it can be air. Then so what does MAC do is the medium access control. It does two jobs. One is that the wireless medium is a broadcast medium, so anybody sends a packet basically, and let's say everybody starts transmitting on the packet. It will be basically, there will be collision, right? It's like a road. If you, let's say if you have only road for one car and two cars come, then there will be collision. So basically the road is a shared medium, right? So similarly wireless is a shared medium. So who should access the road when? That's the basic idea behind the medium access control. Second thing is it also provides addressing mechanisms, right? So if I'm sending a packet from, let's say, the access point to node A, node B will also receive it, because it's again a broadcast medium. So what will MAC do is it will check what is the destination address, and then it will find that okay, the packet was actually for A, and the packet is not meant for me, so it will just drop that packet. So here are types of MAC protocols. So you have channel partitioning protocol, of fixed assignment protocols, then you have random access protocols, then you have demand assignment protocols. So I will very quickly go through them. So you might already know some of them. So the channel partitioning protocol, like TDMA or time division multiple access. So here we divide time into let's say different slots, and then we say that one user can use a particular slot, and this can then happen repeatedly, like periodically, in some way. So in this particular slot, only one user can transmit in this one, second user will transmit in this third. So only one of the user is transmitting in each slot. Similarly, in FDMA, you are using one of the band, or basically one of the channel, and in code division multiplexes, you are using the signal over the complete frequency and time. But what you are doing is you are using an orthogonal signal. Okay, so CDMA is basically each code corresponds to is basically orthogonal to the other code. So if you code basically the signal and add the signal and send at the receiver, you can again get back because of the orthogonality of the signal. Okay. Then you have space division multiplexes, where basically you can reuse the spectrum which was used here, or the resources which are used here, because by the time signal come from this cell to this cell, because of the distance, the signal has died down. So basically there will be no interference. So I can reuse in space, or basically a very good example for this is your FM station. So each city will have the same, let's say, radio stations uh, working or broadcasting on the same frequency, and they don't interfere with each other because the distances are far. So this is a quick, like a idea that in FDMA you are using the frequency, one chunk or one channel or one band of the frequency for all throughout the time. In TDMA you are using the complete frequency band, but you are using only one slot. In CDMA you are using both, let's say time and frequency completely, but you are orthogonal in basically code. So the random access protocol, the one issue with let's say the this kind of a channel partitioning protocol, a fixed assignment protocol, is that let's assume that there is only one user, right? So let's assume that there is only one user which is active, all other users are not active, they don't have any data to send. So every time one has to send, it will come, it will transmit its data in this first slot, and then wait for another 5 slots, and again basically again send in the slot number 1 in the next frame, right? So although it has a lot of data to send and all other slots are empty, still this fixed assignment protocol basically would lead to a lot of wastage in that sense. So what random access protocol does is that it has very simple protocols like aloha. Whenever you have data, you just send, you don't care about anything else. Okay, so if the data goes through, good. If it doesn't go through, then you again resend after some random delay. So it works very well for lightly loaded network, but let's say if the network load increases, then there can be something like this, there where there will be overlap between different transmissions, and basically there will be corruption. So basically it's called as collision. The basic idea would be that if there is a collision, then none of the receivers can decode the data. So to improve Aloha, you have slotted Aloha where you can only transmit at the end, at the starting of a slot. So you have basically the time is divided into slots, and you only try the transmission at the start of the slot, and that you do the transmission with probability p, and with 1 minus p you don't transmit. Okay, that with that probability you don't transmit. So basically you can see example here that there are three nodes which are trying to send data. But they try basically they transmitted in this slot and nothing happened. Basically collision happened, and in the second slot with 1 minus p probability they didn't transmit. Each of them with 1 minus p didn't transmit, and then again in this there's a collision, and only in the fourth slot there is success. Okay, so this requires time synchronization between the nodes. Okay, so because the slot boundary, how will people know what is the slot boundary? So when I say synchronization, it means that they need to exchange information among each other, right? Even one very good example of synchronization is that all of us have a notion of time, right? Because we are all of us are wearing a watch, right? And even for the seminar, everybody kind of had a lot of email exchanges, what time to meet and where to meet and all, right? So the fixed assignment protocol generally has this issue that you have to do a lot of overhead. Then you have carrier sense multiple access, where the idea is that you will, before you transmit, you will listen to the channel and see whether somebody is transmitting or not. So basically only transmit if the channel is idle. Still collisions might happen. That assume that you have A and C who want to transmit data, and when they have packet to transmit, they are checking at that particular time it's free, but let's say when they transmit, the collision may happen at B. Also you might have a hidden node problem that A and C want to send data. When they try to check the channel whether it is free or not, they can't listen to each other because of the, let's say, a big wall in between, and again the collision might happen at the receiver B. So if there's a collision, definitely what you need to do is you need to back off with a random delay and transmit again. So hopefully because of the random delay, A and C will not transmit at the same time. Okay, so there is also CSMA CA. So CSMA with collision avoidance. So here what we do is we send this ready to send and clear to send messages by the source and destination, which will tell the people around or the nodes around that the transmission is going to happen, so they should defer any access. Then the issue, I already talked about the issues in fixed assignment protocols. So the issue with the random access protocol is the collisions, right? So let's say every time I try, but if the traffic is high, then it's like having a jam if the traffic is very high. So the demand assignment protocol is it takes care of both the issues in a sense. So what it yeah so there are two kind of things like taking turn protocols, basic sorry okay so what it does is like one example is polling. So what polling does is that there is a master which will poll each slave whether it wants to transmit data or not. So whichever slave wants to transmit data, let's say, will tell master, okay, I want to transmit data, and then that slave only will transmit data for a particular time. After that, the master will ask another, let's say, node. So, so this eliminates the what is it called as empty slots in channel partitioning. So if you take example again of 1 2 3 4 5 6, that 6 nodes. So in that case, what will happen is it will ask the first node, do you want to transmit data, and first node will transmit, and it will quickly ask second, third, fourth, fifth, sixth that they want to transmit or not, but they will say no, and then the control will again come back to the node 1. Okay, so although there still we need a polling interval, but the polling interval is much smaller than the one slot duration. So definitely that helps in reducing wastage. It also eliminates the any collision, because now only dedicated access has been given, right? The only issue is that what if the master node fails? Okay, so that's the issue, and again there's still delay in polling and how to organize things and all. So this is used in Bluetooth and 802.15 protocols. So again, this is token passing, slightly decentralized version of polling. So instead of master, there's a token here. So there's no node which is master here. So whichever, let's say the node has token will have access to the channel, and whoever does not want just will keep passing the token. So that's the basic idea. The only issue is that there may be node failure where the node can get stuck, or some node might not release the token. Few other things like duplexing methods. Duplexing, what it does, it tells you how the channel access is happening for transmission and reception. So if you are transmitting from A to B, so how is the B to A going to talk to you? Okay, so forward and reverse channel, how you are going to do. So this is basically over transmitter. So this is in time division duplexing, where again you are dividing time into, let's say, in each frame you have two slots. One is for transmission and one is for reception. Instead of that, if you want to keep transmitting continuously and also receiving continuously at the same time, you can use two different frequencies, which is called as FDD. And you can also have hybrid channel access, in the sense that this was non-hybrid, where you are transmitting on one channel and you are receiving in one second channel continuously at the same time. But you can also have time and frequency slots, where you can basically mix the two methods, CDMA and CDMA. You can also have basically CDMA on top. That's what hybrid channel access is. Then these are the network topologies. So the bus and ring, again you can see that this bus and ring are also, although they are wired, they still are shared channels. Okay, uh, right. So but these are wired topologies and these are wireless topologies. So in star, what is happening is the node cannot talk to another node, so directly it has to go through the master or the coordinator, or and then you have a mesh where anybody can talk to anybody. Okay, and then this is a hybrid, and then this is a tree structure. Now, what are the factors contributing to energy waste and expense? So energy is basically consumed in transmission. So if you want the data signal to go for long range, then you need to pump more power or more energy. So definitely it will consume more energy than if you are on higher frequency. The higher frequency, there's more attenuation as compared to the lower frequencies. So the signal does not go that far as compared to the lower frequencies. So if you want, let's say, the signal to go more distance, then again you have to pump more power for higher frequencies. Then if you have more bandwidth, then you have more data processing, which will again consume energy. So if I now talk about energy waste, then there is excessive overhead, especially for fixed assignment protocols, to even define where the frequency boundary is, where the time boundary is. We need to pass on a lot of messages back and forth, and we need to tell, like the overhead is also pretty big, in the sense of the header is also pretty big. So that is something, the overhead, right? Excessive overhead. Second is idle listening. So if you take an example of random access, or let's say CSMA CA or slot, let's say Aloha, their transmitter will send data whenever it has data, right? But the receiver does not know when it's going to transmit. So what it has to do is it has to always listen, keep listening whether data has come, right? So that this idle listening again consumes a huge amount of power. I think half of the energy goes into just into idle listening. Then you have overhearing, where I had taken example where, let's say, the access point is sending data to the node A, but node B is also hearing it, because at the physical layer it does not know what is the destination. So it will process at the physical layer. It will come at the MAC layer and it will try to check the address field, and then it will understand that the packet was actually for node A, not B. So then it will just throw that packet away. So this is what is called as overhearing. So you are trying to process a packet which is not for you. So again, this is the energy wastage. Then packet collisions and retransmission. So basically, whenever the packet, you transmitted a packet and it went in a collision, so you need to retransmit the same signal again. And generally, like this kind of collisions will, the number of collisions increase, the number of retransmissions increase, and number of retransmissions increase, the collision will again increase. So it's like a vicious cycle, especially at a high load. Okay, so what are the ways to reduce energy waste or consumption? So the basic idea here is that, like, based on the discussion just we had on the previous slide, uh, so we can easily say that if I reduce the frequency of operation, basically my energy would be, the energy I will need is less. I can also reduce energy by reducing my data rates. I can by bandwidth, reducing bandwidth or reducing coverage. Then one of the most important thing, and one of the most important thing to save energy is sleeping. Okay, so something very amazing, that whenever you have data wake ups, send, basically turn on your radio, send data, and turn off your radio. Okay, and so basically, by having low duty cycles, you can really increase the lifetime of let's say the node and the battery. Um and the duty cycles can be as low as 0.1%, which is pretty low. So then you have energy saving protocol. So let's assume that if you have schedule, then you are reducing the overhearing and idle listening. And if you have contention based, so schedule based can be very useful, especially if the data, basically the channel is loaded or there's a lot of traffic. And the contention based can be very useful when the traffic is less, because it has less overhead and it does not need any synchronization across the devices. Okay. So let's come to the communication techniques. So there are several communication techniques for IoT based on the network of choice, and generally these are classified based on the coverage, the range of operations. So you have here proximity. Okay, one more thing to keep in mind is that this kind the classification here is not very accurate. Okay, because it's a lot of people have tried to do classification, so there have been many terms, so it's not, the terms are not very precise. Okay, so you have proximity where the distance is very less. RFID generally and NFCs fall into this, so they will communicate only when the distance between the transmitter and receiver is like 10 centimeters. So then you have wireless personal area network where you have Bluetooth, where the range is hardly 10 meters. Then you have wireless LAN where the range is 100 meters. And then you have cellular where the range can go from 5 kilometers to, let's say, 100 kilometers. And you can see there are several, let's say there are several, these are the technologies, and there are several technologies. Today we will very briefly look into this ones: Bluetooth, Zigbee, basically, and LoRa, and then NB-IoT. And we are looking into them because billions of units are getting shipped every year. So they are very popular. Zigbee, Bluetooth, and Wi-Fi are very popular. And LoRa is a actually technology for IoT. This is low power, long range, low power technology in unlicensed band. And then you have your NB-IoT and LTC machine type communication, which is licensed in licensed frequency. So the first one I am starting is the wireless body area network, which is I will say the main application has been the health, and it operates near, basically, very close to the body, on the body, or inside a human body. So you can see here the example for inside the body sensors are pacemaker and cochlear implants. Then you have blood pressure ECG on the screen, and then you can have, let's say, something like temperature, which can be measured slightly, in the sense, slight distance from your skin, right? And all this basically sensors will send data to a hub, and then the hub will send data to a central controller from where the, let's say, a doctor or clinical person can monitor the health parameters of a person. Even the emergency people can also monitor that, and if needed, let's say if the user can also monitor his own data. So the wireless body area network, like there are the medical applications are the most important ones, and primarily the applications are, I will say, in health, like vital sign monitoring, respiration monitoring, glucose monitoring, ECG, hearing aid. But it also helps in disability, like speech disability or muscle tension monitor and all. It can also be used for non-medical applications. So just like gaming, very interesting that let's assume that you have bands, different variable bands, and you are playing some video game using actions. Okay, just like I think I don't play that much game, but at least know that Xbox and all have variables which you can actually use. So that can also use basically wireless body area network. So these are the different wireless body area networks. So this is a level 1 intra band. So basically, this is on one person. Let's all these sensors are one person, and then you have a hub here which is collecting the data, and this will send data to access point. And you can see that it's an inter-band communication. So basically, there are multiple bands here which might be communicating to each other, and then this is beyond band communication in the sense that ultimately data has to be sent to the, let's say, doctor or telemedicine server or ambulance, right? So it has to then connect through, let's say, Bluetooth, wireless LAN, or some kind of cellular technology. So regarding the wireless body area network or the applications, similar applications, there's a technology IEEE 802.15.6 which is specifically for wireless body area network, or then there's a Bluetooth Wi-Fi IEEE 802.15.4 which also caters to this particular domain. Okay. So let's look at 802.15.6. So it has basically three physical layers. One is narrowband, ultra wideband, and human body communications. So and these are the different frequencies. So MICS or medical implant communication services, and then the wireless medical telemetry services. They are basically licensed band, and then you have ISM band, which is basically again this is unlicensed. Then again there is a unlicensed black one in the 5 gigahertz, and then you have this UWB band, the yellow ones. This is the lower band, and this is the higher band. These are the basically the different modulation parameters for the narrow band for different frequencies. So you can see that differential modulation is used here, and the basic idea is that it does not need the full channel state information and makes the receiver simple. And the data rates are going from, let's say, 60 kbps to 500 kbps, or the information data rate. Yeah. On the other hand, you have the ultra wideband, where the idea would be to use very short pulses and large bandwidth. So basically, it can go up till 500 megahertz. So here I'm trying to make a distinction between the three types of bands. So narrow band is basically if the bandwidth of the signal is much less than 10% of the carrier, it is called narrow band. If it's in the range of, let's say, 10%, it's called wideband. And ultra wideband, it's like it should be more than 10%, around, let's say, 20, then it becomes ultra wideband signal. So in this particular, using ultra wideband, you can see it's pretty big bandwidth, 500 megahertz, and then the data rates are from 0.5 mbps to 10 mbps. And the good thing about this is it's low power, low cost implementation. Then we have third kind of physical layer, which is it's not actually wireless. So here our human body is being treated as a transmission medium. So it's kind of a wired kind of thing, in the sense not exactly wired, but yeah, it's like it's not wireless. So and here there are two frequency bands centered at 16 megahertz and 27 megahertz of bandwidth 4 megahertz each. There are two ways of doing human body communication. So one is using capacitive coupling, the other is using galvanic coupling. And in this particular standard, electrostatic field communication or the capacitive coupling is used. Then here are the MAC protocols. So you can see the support the so there's a beacon mode with super frame boundaries, and there is non-beacon mode with super frame boundaries, and then non-beacon mode without super frame boundaries. And then there are different mechanisms. So it has mixture of like different I will say access schemes. So there is slotted Aloha. You can also use CSMACD. You can also use polling. Okay. So there's also basically polling. So this is the super frame structure, where basically this is a super frame structure with beacon. So beacons are sent beacon like once in a while you are sending beacon so that everybody knows what. So this has the information related to the, let's say, the main coordinator and the network. So you have different kind of phases here. One is the exclusive access phase. Basically, only higher priority data can go in this particular slot. While the random access phase and condition access phase, it's for regular data. Then type 1, type 2. So in this EAP, RAP, and CAP, you have you use CSMA or slotted Aloha. So you use contention based access. On the other hand, type 1, type 2 phase, you use polling. Okay, so then also there's the 3 levels of security. I will not go into that much into security. Let's skip. So then we have IEEE 8.15.4. A lot of people also know this by the name Zigbee. Okay, and this is being pushed by big giants like Google and Amazon, and this is very popular in wireless sensor network and with the applications of consumer and building automation and industry. And this is so this is generally used for wireless personal area network. Let's say the range is around 10 meters. The traditional use has been 10 meters and 200 meters. And the idea has been to have low power, low rate, and low cost wireless communication. So generally, there's a confusion that this is Zigbee and IEEE 8.15.4 are same, but they are not. So basically, they are complementary. So this 15.4 defines MAC and physical layer, while Zigbee Alliance defines the application and network layer. So again, the Zigbee uses different kind of access schemes. Like it has a slotted CSMA, and it also has guaranteed time service. So guaranteed time service is like a scheduled or fixed assignment protocol. And so you also have non-slotted CSMA or no beacon mode. And on the physical layer, there are 3 frequencies: 2.4, 915 megahertz, and 869 megahertz. And basically, the data rates range from 20 kbps to 250 kbps. So what is important to also understand is that the 15.4 only defines MAC and PHY, and different applications let's say are building on top of it. So you have Zigbee, you have 6LoWPAN, thread, which is basically aggressively pushed by Google. All of them are actually building on top of this 15.4 standard. So these are the different frequency ranges. So this is sub 1 gigahertz, basically less than 1 gigahertz. So keep in mind that for 1 gigahertz, the coverage will be much more as compared to 2.4 gigahertz, because attenuation is more in the high frequency range. So this might have this is like the range can be 100 meters to 1 kilometer, but here it can be 10 meters to 100 meters. These are the different modulation scheme: BPSK, QPSK, and the data rates are around 20 to 20 to 60. Sorry, data rates are 22 to 50 kbps. One more thing is that it also uses CDMA on top of this modulation scheme, BPSK and all. So this is the network topology. It uses all of them: star, mesh, and cluster tree. And then Zigbee uses 16-bit addresses. So each PAN or personal area network can have 65,000 devices, which is pretty big for a network. Okay. Basically, the generally the coverage of Zigbee kind of a network would be not more than 1 kilometer. So, I think 65,000 is a pretty big numbers which can be supported. So these are the key IoT features for Zigbee. So for low power, millijoule and microjoule, and then large coverage, especially for 6 gigahertz. and it's easy to install and maintain. Mesh is a very powerful self-healing protocol. So even if some of the nodes basically fail, it rearranges itself, because anybody can talk to anybody in the mesh basically uh, format or topology. Then it can support thousands of nodes, and there are many suppliers, so the cost is pretty low, and the battery life, this can run years on the battery, secure. The only issue is that there's no mobility. So if I deploy let's say a Zigbee or 15.4 kind of a network, and if I go out of, let's say, just 1 kilometer away, suddenly there will be my device will stop working, and definitely less coverage in 2.4 gigahertz. Then let's talk about the Wi-Fi. So here, so generally Wi-Fi is used for last mile connectivity, broadband internet, right? Most of us have nowadays Wi-Fi at our home, and the most important application would be the high data rate applications like browsing, audio, video, gaming, right? And the speed are also in Gbps. So till now, the Wi-Fi where the names were given like uh, 8.11b, A, G, N, A, C, A, D, right? And so now they have changed the nomenclature, so they are also going something very similar to the cellular, which is going from 1G, 2G, 3G, 4G, 5G. So now you have the naming like this, where 8.11 AC is 5G, and let's say AX is 6G, and you had your B, which was 1G, A was at 2G, 3G was 3G, and all, N was 4G. So so what we have just seen till now has been that each generation the data has only increased, okay, but looking at the IoT market, which is going to be in let's say tens of billions of devices, so this, like the Wi-Fi also started kind of adapting itself to IoT network. So what they did was they converted their 8.11 AC to 8.11 AH. Okay, for this basically caters to IoT market, and this was the original thing. So why they did just adopt AC, they modified AC to get AS is for faster standardization, because then already AC was standardized, so it becomes very easy. Just scale down everything, and then you get your Wi-Fi technology or Wi-Fi standard for IoT. So keep in mind that the applications for AC and AH are different. The bands are different. First of all, the bandwidths are different. Then the applications are different. The data rates are very different. So I will say the internet, you are not expecting to send data in Mbps and Gbps. You are only expecting data to be sent in kbps. Again, you are not interested in sending continuous data. You just are sending once in a while. Let's say one packet in 15 minutes or 5 minutes, like that. Intermittent. Then the distance in wireless LAN, let's say you would be interested ki, okay, just connect devices in my house. But in IoT, you would want more coverage, and keep in mind that your the traditional Wi-Fi point wouldn't support more than 20 devices at the same time. But here, as I said, have been discussing, we need more number of devices to be connected to the same access point. The location again, mostly the wireless LAN is indoors, but for, let's say, for IoT, it can also be outdoors. And keep in mind that this 802.11ah is not backward compatible with the other generations of Wi-Fi, ABGN, right, and AC, because it's totally on a different band. Okay, and the technology is also slightly different. So, okay, so what the way AH has been adopted from AC is that scaling down everything. So as I said previously, that the bandwidth has been reduced 10 times. So now the power consumption energy consumption will go down, and also then we have repetition coding. The things have been simplified a lot. Okay, so that helps a lot. Helps again. Okay, these are frequency bands. So basically, these are all ISM bands in sub 1 gigahertz. So US has the most amount of spectrum of around 26 megahertz. Europe has around 5 megahertz, and then China has around 13. Okay. So this network topology is the only thing is the nomenclature is slightly different. So the nodes are called as stations and cluster is called an access point, but it's the same. Like it also supports, so the Wi-Fi supports all kind of different kind of topologies. Okay, so very quickly I would like to tell that very similar to the cellular communication, Wi-Fi is going to integrate IoT as well as let's say the traditional application of broadband internet in the one standard in 802.11ax. So these are the key IoT features. First is the high data rate. So if you see that other technologies like Zigbee, Bluetooth, and let's say I will talk about LoRa also, the bandwidth is very low. So they will not be able to handle applications like video camera, images, and all. The range is long, around 1 kilometer, and it can scale to thousands of nodes. And the most important thing is widely used, right? Wi-Fi is like everybody uses. Each phone has Wi-Fi and all. But the issue, yeah, this is something I really find very interesting that most of the world is actually using Wi-Fi on 2.4 gigahertz, and AH and AX both are on different frequencies. AH is on sub gigahertz and AX is on 5 gigahertz. So there is going to be some problem there. One more big issue is that although standard is available, but there are no products on AH, and people are continuing to use, let's say, the uh, power consuming standards like BGN for IoT. They might do some tweaking here and there for saving power, but the point I'm trying to make is that they are not using a standard which has been designed by the IEEE 8.11 standards body for IoT. So this is very surprising. Security, so it's not that they don't have use encryption, it's just that Wi-Fi is so popular that hackers tend to attack that, uh, because there is a lot of gain. Even if they crack one, then they suddenly have many more which they can let's say target, let's say use cases they can target. Yeah, and definitely power consumption is high and there's no roaming facility. BLE. So maybe I will very quickly wrap it up. Like few, I just want to give you a highlight what is happening here. So BLE again, if you go from versions 1 to 3, the BLE. Okay, what was the BLE generally used was for this kind of Bluetooth. Basically, it was just a wire replacement communication protocol, and for low power consumption and with very low range, short range and low cost transceiver, right? So applications have been like home studios, MP3 players, or headsets and mobile phones. So in the first three versions of the Bluetooth, the idea was just to increase the data rate. In the fourth one, BLE was adopted, which basically is for IoT applications where the basic idea again is to serve intermittent data once in a while and increase the coverage, reduce the data rate. And again, there's a version 5 of that, which is a better version than version 4. Yeah. So keep in mind that again, very similar to the AH thing, the BLE is not backward compatible. So it is not backward compatible with the earlier versions of Bluetooth, and yeah, and in till now the mesh was not possible, but now it is possible. So like I'm saying, the earlier it was not possible. BLE only had Piconet. Again, the topology, the names are different. Like this is called as master, this is called as slave, and this is called as Piconet instead of star. Just that, yeah. And then this is called scatternet. The clustered tree is called as scatternet. Yeah, but the topologies, all topologies are now applicable. So, again, this is a quick comparison that this is for audio, video streaming, and but BLE is more for data transfer once in a while. This is also used for location services, localizing where, like what where are the persons or where are the services, particular services. Okay, so I will skip this. Okay, what are the IoT features that extremely low power, and the main thing is that it's heavily used. Bluetooth is heavily used in especially lighting and home automation, and it has like the size is pretty small, cost is small, and then security is also good. The issue is that it's pretty low range. Okay, like it says 10 meters, but it will not even work properly for 10 meters. BLE might work, let's say till let's say 100 meters. The data rates are pretty low, so it can't support any voice or video capability, the BLE part at least, and then obviously roaming is not there. So then let's talk about the cellular 2G, 3G, 4G, 5G. So all these technologies, again, you can see that till 2G to 4G, the focus has been to only increase the data rate for each user, right? But now looking at the market, again, everybody is trying to adopt to IoT market because they don't want to lose such a big business opportunity. Okay, so basically since release 8 or in 3G, they started integrating or started looking at IoT and started modifying the standard so that it also suits the IoT market. So in release basically 8 of 3G, we have LTCAT1, which has 10 Mbps, and the latency is 50 and number of antennas. So here, hello,
Yes, sir.
yeah,
Continue, sir. Nothing, sir.
okay. I heard something, so that's okay. So basically, and then you can see LTCAT 0, which came in a later release, and then you can see here in the basically in the 4G. So the data rate was again reduced by 10 times. Okay, and number of antennas again like reduced, and the duplex mode was simplified. And again, the receiver chain is only one. So the idea has been to make the receiver simple, okay, to cater to IoT. That's the whole idea has been. And in release 13 of 4G, so LT-CAT M1 and LT and narrowband IoT were also introduced. They have been enhanced in release 14 again. So LT-CAT M1 is backward compatible with the earlier LT releases. NB-IoT is a totally separate standard. It still works in the licensed frequency, and this is mostly designed to compete with, let's say, cellular technologies unlicensed band like LoRa and Sigfox. Okay, you can again see that the data rates have been again slashed almost 1/4 of this 1 Mbps, and again 10 times the bandwidth has been reduced from 1 to it has been brought to 180 kilohertz, and we are only using the same one receive chain and half duplex. Okay, so the idea has been to keep making simple receivers for IoT applications. Yeah, so I already talked about them, and then yeah. Right, so I also talked about them, and then just wanted to say that this is mostly to compete with the Sigfox and LoRa, and this is not compatible with the other 3G, 4G devices. The good thing is that you can actually put in any license band. It can be in guard band, in LTE, standalone deployment, GSM also we can do implement. Okay, so if you see the first 4 generations of the cellular technology have been focusing to connect people. Okay, the focus has been always people, but in 5G the focus is going to be on people as well as things. Okay, that is something a massive change in the design philosophy itself. So in 5G there are going to be three main, let's say, topics. Out of that, one is massive IoT. So 5G and cellular operators don't want to miss that, as I said, a big market. So they are changing or adopting the IoT market, adopting for IoT applications very heavily. And some of the use cases are very interesting for 5G, especially. I will say that take an example of telemedicine or virtual remote control, let's say, operation, right? that kind of application needs very low latency, high speed communication, which only 5G can offer in all, I think I will say, in all of the communication technologies which we have discussed. Okay, even the LoRa does not even have any capability to handle audio or video. So but 5G is going to be a game changer there. Okay, so so still I'm saying, anyway, let's discuss. So real time monitoring and all this kind of applications, 5G is going to be very important in healthcare. Okay, what are the key IoT services? So first is the quality of service, because it's a licensed band. Till now, most of the, let's say, technologies are working on unlicensed band. Why would technologies want to work on unlicensed? Because license cost a lot. Okay, they cost billions of dollars. So the solution becomes costly. So that's the reason people want generally keep in unlicensed. But the problem with unlicensed is that anybody can interfere with you. So in license band, only you are transmitting. No, there's no interference. So the quality of service is the best. Even cellular things give you very low latencies. One more thing is that always the security protocols are always updated. Um, you can see that 256-bit, which is the encryption, which is the best in class in the sense in any of the communication technologies, and it's ubiquitous in the sense that it's everywhere in the world. You go with your device, hoping that it has a roaming feature and it will work anywhere in the world. Uh, Again, it's scalable. We have seen that it's scalable, and it's still connected even the power goes, right? If power goes, then your Wi-Fi will stop working, but this will not, because your base station is still on. Yeah, the issues is the cost. Definitely the license is huge, like very costly. It really inhibits any startups to get into the let's say this kind of market. And then capex and opex are huge. So subscription costs are also high. Power is high. You need to keep changing your battery, and it's not possible to make your own network. So Wi-Fi, you can make your own network. Zigbee, you can make your own network, but here you can't, and you have to always keep paying subscriptions. So LoRa, I will take maybe I will just 1 or 2 minutes. I will take on LoRa, and then I will wrap up. I will wrap up very quickly. It's almost 1 hour already. So LoRa is a very interesting, basically technology. It is meant for long range, low power IoT applications, and interestingly, as compared to others, it has been designed for IoT. Okay, from start. So it has this star of star topology. Uh, So as I said, this is a very long range in the sense it can 10, 15, 20, 50 kilometers also it's possible. Okay. So so you would say that already I have so many wireless communication technologies already for IoT. Why would I need a new technology altogether? Right, but I will say that this kind of, there are applications like ultra marathon runners, where you want to keep track of the health of the, let's say, marathon runners who might be going big distances. If you want to keep track of a dementia patient monitoring, because many times you must have heard that, let's say, a person is old and he goes somewhere and he forgets where he lives, right? So that is a big issue. Even monitoring COVID-19 and quarantine patients, that they should not be moving around, so that helps. Basically, this kind of a LoRa kind of a thing can help there. Again, skiers who basically, and people who are going in mountains and all, you might not have any other coverage. Even the, let's say, 3G 4G coverage might not be there. So this kind of applications are there. Okay, so let me only take one slide on this now. This one. So it has very interesting architecture. The basic architecture here is that you have multiple gateways and you have end nodes. End nodes are dumb nodes in the sense that they just transmit. They don't see where is the base station. They don't see where's the gateway. They just transmit the signal, and whichever gateway is in the vicinity, it will collect the data. So this topology is called a star of star. Okay, so you can see here that this one, the meter is actually transmitting, and this two gateways are in the vicinity. So both of them are listening to this particular node. Okay, and what happens is that now you have multiple copies, so the network server will do all the filtering of any redundant copies. Okay, and so that way these are pretty much very convenient to deploy. You don't need to worry about any network to be set or topology. These issues are like, so very nice architecture, very simple architecture. That's the reason it's very hugely popular. And it has a pure Aloha and chirp spread spectrum. For modulation, it has this, and then the access is pure Aloha based. And it also has security, two-level security, so that the gateways don't decode the message, because otherwise anybody can put a gateway and start collecting data, but only a network server, authentic network server, will decode and clean the data. Yeah, so low cost, very the wide coverage, low power sensors, I will say one of the best for that. The only issues are here is the payload. Payload is very low and the duty cycles are also low. You can't transmit more than, let's say, some cases you can't transmit more than 1% of the time. You can't be up more than 1% of the, let's say, time. Then it's using unlicensed, so there's already too much crowding. You can see that all of them, you saw that most of the technologies are already on the unlicensed band. So there's going to be issue, and you can't use this for real-time monitoring. There's too much latency. So this is kind of a comparison of all the technologies I have talked about, and I'm here assuming, kind of assuming that ban also is somewhere, let's say, in the personal area network and personal area network. So you can see that the best frequencies are the sub gigahertz. The LoRa has this, works on this, and again you can see that the other technology is also doing that. Then the LoRaWAN has a very nice topology of the star of stars. Mesh has pretty robust, I will say, topology, but star of star is like helps in making things very simple. The range again is very important, and the power again. LoRaWAN has the least power, and number of devices supported are also pretty high in all of them. Then the data rates are different, so you can see the data rates are different here, and all of them have some power saving mechanisms like sleep wake schedule, different frequencies, and different power or sleeping patterns. Yeah, I'll not go into that, but yeah. But one thing I wanted to say is that one size does not fit all. So basically, what it means is the different applications have different requirements. And issue is that the IoT is very broad. So you can see here that there are so many different applications having different requirements. So one particular technology is not going to cover all of them. Okay, so I will say this is what is going to happen in the communication for IoT domain. Even for health, you can see that there are applications which are totally different. One is pulse meter, then you have wearables, then you can have very, let's say, low latency urgent medical care, right? That will come here. So the idea would be that different, let's say, technologies would complement each other. They will compete with each other, but they will also complement each other in different spaces. That will be the main, let's say, I will say, takeaway you should take from this particular presentation. Let me only in another, let's say, 3 slides, I will wrap up the presentation. I just want to tell what are the different activities I am doing at IIITH. So we have one project on IoT enabled smart cities, pollution, health, and governance, where we are trying to understand what is the effect of pollution on health. And here the idea is to basically deploy a very dense network of dense IoT network for determining the air pollution, and then also collect health surveys of and we are targeting specifically traffic police who are standing there 8 hours a day in a peak pollution. So we are trying to understand how the pollution affects them, and we are also trying to understand the other target group is school children who are very sensitive. Okay, and this is a multidisciplinary project with different faculty from IIIT and also one medical doctor in coming in the picture. Then we have Center of Excellence on IoT for Smart Cities, and this is supported by India EU collaboration on ICT standardization. TSDSI Indian Telecommunication Standards Body, and HC again it's European Telecommunication Standards Body. and I am the coordinator for that this Center of Excellence. And again, several faculty from IIIT are participating in this. And the activities which are supported in this are knowledge initiatives, research collaborations. So last year, one such research collaboration, basically one delegation went from IIIT to La CNRS in France, and which have resulted in this Living Lab project. It's a very ambitious project, very interesting, and I will say this is the India's first living lab for smart city research. The basic idea is that this is our IIIT Edge campus, and we want to deploy several IoT applications in the campus. So we want to convert we want to make our campus smart. Okay, so different themes have been targeted like water, health, waste, safety, energy, right? And this project, this is pretty big project given by the Ministry of IT and Electronics and IT. And again, several faculties are involved, and this is in collaboration with European Business Technology Center, Indian Smart City Mission, state government, central government, and European universities, and this Amsterdam Arena. And these are the objectives. The first one is to do research on IoT for smart cities, and then IIIT is very famous for basically AI/ML kind of research. So we want to again generate data for that, and we are hoping that this will result in AI/ML applications for smart cities. Then this will also serve as a test bed for any startup or a company who wants to try their solutions. Okay, so we have very nice vibrant campus of around 3000 let's say resident, so basically 2500 residents and 1500 visitors coming daily inside the campus. So and this is just a 66 acre, so basically a very nice environment, a live environment, but still slightly under control, right? So so people can actually come and try the solutions here, and then they can take the solution to the on the city level. Then again, idea is to promote startups in the space of IoT for smart cities. So these are the references, and with this I would like to thank you very much for your attention, and if you have any questions I would be happy to answer them.
Sir, thank you, sir. Sir,
Thank you.
is this audible, sir?
Yeah, yeah.
Sir, can you see the chat box in your
Okay.
window, sir? Can you able to see?
So I will should I? Yeah, I can see one question. So
Yes.
which communication protocol most likely used for IoT application? So as I said in my, let's say, the summarizing slide, that it depends totally on what is the application. So based on the application, you will have to choose your let's say the technology, because no one application will be let's say fit everywhere. So let's assume that cellular like 5G, right? 5G might be fast, fine, but then it will not be low power. Okay, so then if let's say, so if I want to monitor temperature, do you want to use 5G? It doesn't make any sense, right? So there something like LoRa or Wi-Fi or Bluetooth might help, where we don't care about the latency, because every 5-10 minutes if I'm monitoring, that's okay. But if you are monitoring something like, let's say, as I said, telemedicine or remotely you're trying to do some operation, then you want 5G, or let's say very high speed kind of a network, low latency network. I hope that answers the question.
Definitely, sir. Thank you, sir. Thank you for sharing your knowledge with us, and thank you for spending your time with us. And also, we have received a very good session and really informative. Like that, the participants is given the put it in the chat box. I think the participants have a good session with you, sir. Thanks a lot. Thank you very much,
Thank
sir.
you. Thank you. Thank you, everybody.
Now, yes.
So if there, I just want to say one thing. If there are students who are looking for some research opportunities, we are actually looking for interested students who might be want to work on this living lab thing. Okay, so thank you, madam. Yeah, thank you, everybody.
Thank you, sir. Thank you, sir. Participants kindly attend the afternoon session and kindly you join by 1:50 p.m.